Example, dual combustion engine. An ideal dual cycle with an air as the working fluid has a compression ratio of 18 and a cut-off ratio of 1.3. The pressure ratio during the constant volume heat addition process is 1.1. At the beginning of the compression process, the air temperature is 35 degrees Celsius. The mass of air throughout the cycle is 0.1 kilogram. Sketch the cycle on a PV diagram and determine the amount of heat addition at constant volume in kilojoule, the amount of heat addition at constant pressure in kilojoule, the network of the cycle in kilojoule, and the thermal efficiency in percentage. Also given to us is the value for the specific heat at constant pressure and the specific heat ratio for the air and constant throughout the cycle. First, we are going to draw the PV diagram and list out all the informations given by the questions. Note that for dual cycle, it looks like it is a combination between the Otto cycle and diesel cycle. The heat addition process will occur in isochoric process and also isobaric process. Meanwhile, for the heat rejection process, it is still in isochoric process. The informations that we have from the questions are compression ratio, cut-off ratio, pressure ratio, the initial temperature, the mass throughout the cycle, the specific heat at constant pressure, the specific heat ratio, and we can use the formula of specific heat ratio in order for us to find the specific heat constant at constant volume. For process 1 to 2, we are going to use the isentropic relation to find the value for temperature at state 2. Next, for the process 2 to X, where in this process, heat addition at constant volume, by using the law of P over T equal to constant, we can have the relation of P2 over T2 equal to Px over Tx that can be used to calculate the value of the temperature at state X. For the process X to 3, heat addition at constant pressure process, from the law V over T equal to constant, we are going to use the relation of Vx over Tx equal to V3 over T3 to find the temperature at state 3. Next, for the process 3 to 4, isentropic expansion, we are going to use the isentropic relation between the temperature and volume to obtain the value for the temperature at state 4. Note that V3 over V4 is equal to V3 over V2 times V2 over V4, where V3 over V2 is the cut-off ratio and V2 over V4 is 1 over the compression ratio. Thus, we can have RC over RV. We are going to use these equations in order for us to determine all the items requested by the question. Heat addition at constant volume process, heat addition at constant pressure process, and we know that the network output for a cycle will be equal to Q net in, and Q net in is equal to Q in minus Q out. For dual cycle, there will be two processes involved for heat addition. Therefore, Qin is equal to Q to X plus Qx3. And for the thermal efficiency, we are going to use the formula of net work output divided with Qin.